So that's a very nice story. I gave you a whole rigmarole and I claimed that this is how the sun produces its energy. How would you go about verifying such a thing? You can't get inside the sun. There's hundreds of thousands of kilometers of sun between you and the core where these reactions are going on, which is very good because it prevents all the gamma rays from escaping. And the basic reason we knew how stars worked in the 30s was because Eddington had the theoretical idea, and as I said, Bethe figured out how to get through the weak decay process. But it turns out that we can, in fact, look right inside the sun with a beautiful experiment. The idea is due to an experimentalist called Ray Davis and a theorist called John Bacall, who in the 60s come up with the idea that, wait a minute, one of the properties, one of the products of this PP process that we discussed is electron neutrinos. 2 electron neutrinos for every alpha particle, for every helium nucleus form. And we know how many helium nuclei are formed per second because we know the total luminosity. So we know how many neutrinos the sun produces every second. These neutrinos are produced in the core, but being neutrinos, they sail right through hundreds of thousands of kilometers of sun with essentially no attenuation, maybe 3 interact. It doesn't matter. This is great because this gives us a telescope that essentially eliminates all of the distraction of the sun and lets us look right into the core. The disadvantage, of course, is that they also sail through the Earth and through whatever your detector is, and most of the neutrinos will cause absolutely no interaction. To give you a sense, as I said, 10 to the 11 solar neutrinos hit every meter squared of Earth every second, so you are being bombarded with billions of neutrinos as we speak. Obviously nothing happens. So how do you build a detector such that something will happen? Well, in the 60s, these two guys put together this brilliant experiment where essentially they take a huge tank of cleaning solvent, bleach, which contains chlorine. They stick it underground in a gold mine, and the reason they stick it underground is to prevent cosmic rays and to insulate it from all kinds of noise. And once in a very long while, an electron neutrino penetrating this tank of chlorine will interact with a neutron in a chlorine atom and convert that neutron through the reaction that we talked about, where an electron neutrino plus a neutron can become a proton plus an electron. Through that reaction, this occurs inside the nucleus that converts one of the neutrons here to a proton, that converts chlorine to an radioactive, unstable isotope of argon, a noble gas. Unfortunately, the actual neutrinos from the PP process that I showed, the way it works, would not have sufficient energy to lead to this reaction, but there's some other modes of interaction that do produce high-energy neutrinos, and so one could imagine detecting the neutrinos from those, and if you understand your model correctly, then you can relate how many PP processes go on to how many of these other processes are going on because you understand the rates. You do the calculation, you figure out how many high-energy neutrinos the sun produces. It's a copious number. How many of them hit your detector? It's a huge number. How many of them interact? One argon atom should be formed in this big tank of bleach every 6 days. So Mr. Davis's job is to detect one atom of argon every 6 days. He flushes the detector, looks for the radioactive signature of the argon, which being a noble gas bubbles out. And he's trying to find an atom every 6 days. He empties the tank every couple of months and looks for 15 atoms. And he finds some argon in the tank, but less than predicted. And this is a result that comes out in the late 60s, and over 30 or 40 years, 30 years, I guess, Davis is making these measurements and continually obtaining results that are too small, that do not match predictions. Remember, we know how many neutrinos the sun forms because we form precisely 2 neutrinos every time we form an alpha particle, and that's how we make our energy. So maybe people say the solar model is wrong. Maybe our understanding, of course, we know how many alpha particles are produced, but maybe the details of the ratios of the rates of the high energy and low energy neutrinos are somehow wrong. This is a great incentive for people like Bacall to refine the solar model to exquisitely high precision. Maybe our understanding of the processes in the detector are wrong. In fact, it turns out that the answer is given in 2001 by measurements using the Sudbury Neutrino Observatory. This is a completely different technology. It's sensitive to all different kinds of neutrinos, including the low-energy neutrinos, and if you detect the problem with the flux in those, then you discover that the sun doesn't shine. And so the Sudbury Observatory in 2001 resolves the issue, and what we realize is that what was wrong was our understanding of particle physics. Particle physics again? Yeah, I'm sorry, here it comes. This is going to be a fun story, though. So we need to extend our table of particles. Here, I'm not bothering with the antiparticles because we understand that everything comes in doubles. But here is the list, excluding the photon that I didn't bother to list. Of all the particles we've seen so far, I've added their masses in these units we like to use that we'll discuss later. And you see a neutron is a little bit heavier than a proton as promised. And the mass of the neutrino is effectively zero. It turns out that along with electrons, there are other negatively charged elementary particles, much more massive than the electron, first 200 and then about 3,500 times the mass of the electron. And these are the mu meson and the tau meson. Otherwise, they're for all intents and purposes electrons, except heavy electrons. And each of them, it turns out, is accompanied by a neutrino. So just as an electron has an electron neutrino, there's a muon and a mu neutrino, a tau meson and a tau neutrino. All of the mesons are negatively charged, all the neutrinos are neutral and don't interact with anything, except for the fact that the electron neutrino carries electron number, and we have two analogous conserved numbers for mu number carried only by the muon and his electron, and tau number carried only by the tau meson and his electron. And so, for example, the favored decay mode of one of the decay modes of a mu meson is mu, which is negatively charged, decays to an electron, which is negatively charged, plus, well, electron number has been violated, but not if I produce an anti-electron neutrino, and now muon number has disappeared, but not if I have a new mu, and this is indeed one of the allowed and existing decay modes of the negative muon. So we have all of these particles, and their interactions of electrons, the weak interactions of electrons and muons and so on, conserve not only electron number, but also mu number and tau number. And so, for example, the decay in the sun that converts a proton to a neutron produces not a mu neutrino, but an electron neutrino. Similarly, the process by which chlorine changes to argon can only occur in the presence of an electron neutrino. And it turns out that neutrinos oscillate from one kind of neutrino into the other. In other words, electron, muon, and tau number are not, in fact, conserved, not by the interactions, but by the neutrino propagation itself. Neutrinos spontaneously change from one flavor to the other en route. This is called neutrino oscillation. It's the discovery in 2001. It was, I think, the 2002 Nobel Prize, including Ray Davis for his prediction. The PP process, as I said, produces electron neutrinos. By the time they get here, they've all mixed up, and only a third of them are electron neutrinos. The other 2/3 are mu or tau neutrinos, which do not interact in the way that Davis was looking for in his detector. And in particular, this implies that despite the fact that we thought neutrinos are massless, the question marks on their masses in the previous slide are because neutrino oscillations, and there have been other discoveries of neutrino oscillation since, show us that neutrinos cannot possibly be massless. A massless particle could not oscillate. And so we made, by trying to understand the structure of the sun, well, we got very well-refined solar models. We also discovered a whole new property of fundamental particle physics, and I find that really exciting. We'll meet these neutrinos again. They turn out to be more useful than you'd imagine, but I thought you would enjoy this great story where, after decades, and I remember sitting in conferences where the particle physicists would argue with the astrophysicists over who was wrong, and the net result at the end of the day was that we were wrong and they were right.